What is quantum field theory? Well, I can give a very basic answer to say what quantum field theory is. Quantum field theory is quantum mechanics plus special relativity. Okay, so what do I mean by that? Well, I think you've studied some special relativity before, and you know that the important thing here is Lorentz invariant. In special relativity, you do particle mechanics in a way that is consistent with Lorentz invariance. So when we say we're going to do quantum field theory, what we actually want to do, we want to do quantum mechanics in a way that is Lorentz invariant. The first question we could ask is, where would you use quantum field theory? Well, for us, the place that we are most interested in using it is in particle physics. We want to describe collider experiments where we scatter two particles off of each other. So we're talking about particles. That means necessarily that we're talking about short distances. Actually, a better way to phrase it is to say that all actions in the problem are small. When distances are small, or even better, when actions in the problem are small, then you know you need to use quantum mechanics. By small here, we mean that if you calculated the action of your process, you would find a number that is close to the value of h bar. If you want to think in terms of distances, well, we're talking about maybe atomic scales or nuclear scales. The atom is about 10 to the minus 10 meters in diameter, and the nucleus about 10 to the minus 15 meters, which is about 100,000 times smaller. For elementary particles, well, some of them still appear to be points, but for some of them we've resolved the size, and it's much smaller than the nucleus. So the point is, we're talking about very short distance scales, and that's the reason why we must use quantum mechanics. The second important fact is that when we scatter these particles, we accelerate them up to a very high speed before they scatter. Okay, so let me make a comment. When I say a high speed, I'm always talking about the speed of light as being very big. So when we say we've got a high speed, we mean that we're at such a large velocity that we're close to the speed of light. So we accelerate these tiny particles to close to the speed of light, and then we allow them to scatter. Well, if I'm moving at such large velocities, I must take into account the effects of special relativity. So this is why we have to use quantum field theory. Now, there are many other places where you would use quantum field theory, for example, in condensed matter physics. To do quantum field theory in the condensed matter setting, you probably wouldn't start off by making a statement like we did, that quantum field theory equals quantum mechanics but special relativity. You would start off in a different way. But this is a good starting point for us. So for us, quantum field theory simply means doing quantum mechanics in a Lorentz invariant way. So what's the key idea? Well, it's all about symmetry. Now I want you to think back to problems that had symmetry. Remember when you were studying the quantum mechanics of the atom? The only problem that you could really solve exactly was the hydrogen atom. And what was the simplicity of the problem? Well, it was because the wave function looked like a spherical harmonic multiplied by a function of r, the radius. Why did the problem or the wave function have such a simple form? Well, it had such a simple form because the hydrogen atom problem has a rotational invariance. The Hamiltonian of the hydrogen atom is invariant under rotations, and that's because the potential term is the Coulomb potential, which depends only on the distance between the two particles and not the relative orientation of the two particles. So there's a rotational invariance. And this rotational invariance, the symmetry, simplifies the problem. So in the quantum field theory situation, we want to do quantum mechanics with an extra symmetry, namely Lorentz invariance. If I do quantum mechanics with more symmetry, I should expect this is easier than quantum mechanics without the symmetry. Why? Because symmetry always simplifies problems. So thinking about things based on our past experience, we're tempted to think that quantum field theory is going to be easier than quantum mechanics because it has an extra symmetry. Well, that's wrong. Quantum field theory is harder than quantum mechanics. Actually, it's much harder. And trying to understand why it's harder is a good idea. It's going to give us some insight into the theory, and it's going to help us to build the theory. So to start, I want to remind you that there are two kinds of effects coming from relativity. And then we're going to try to estimate how big these two different effects are. The first effect is something that I would call kinematics. What is kinematics? Well, kinematics is the study of motion. So there's no dynamics. So what I mean is, I'm not telling you a specific force. I'm not talking about a specific interaction. When I talk about kinematics, I'm making statements that are true for all problems. As an example, velocity is always dx dt. That's part of kinematics. And in classical mechanics, acceleration is always dv dt. It doesn't change if you have a different force acting. Acceleration is simply always dv dt. In special relativity, there are some formulas like that. These are formulas where it doesn't matter what problem you're talking about. They always take the same form. And these are the formulas that lead to things like time dilation and length contraction. When you discuss time dilation and length contraction, nobody spoke about a specific force. It was a general discussion. Another formula like this is the relativistic formula for energy, E is equal to mc squared. These are all examples of kinematics. And because of kinematics, we will find that there's a difference between non-relativistic kinematics and special relativistic kinematics. I want to know how big that difference is. The other thing that can happen in quantum field theory is that when we shoot two particles together, so let's imagine we shoot in a proton and let them scatter, well, we might not get two particles out. So at low energies, shooting two protons together might produce two protons, give them a bit more energy. Well, now we shoot in the two protons, and out comes out a proton and a pion, a pi zero. And if I give the two protons a lot of energies, I shoot in two particles, but an enormous number of particles are produced by the collision. This is an effect whose details do depend on the details of the force. So this is part of dynamics. I'm going to call this a multi-particle effect. What I want to know is how big are multi-particle effects compared to the kinematical effects.